So here we go again, guys. Today we talk about section 14.7 about maximum and minimum values, of course, for functions. And this is a kind of application. Hopefully, you're gonna enjoy this. So in this section, we see, in fact, how we can use these partial derivatives to locate maxima and minima of functions of two or many values. Okay? So if you look at this figure, you see how beautiful this figure it is. So you see this is our figure, and look at the hills. You have hills, for example, here you have two hills, okay, where you have kind of valley, sorry, and you have two hills here where you can have detect local maximum and an absolute maximum, and here a local minimum and an absolute minimum. Okay, and we would like to see now visually. Maybe you're not able to figure it out all the time. And we'd like to see what mathematics can bring in this stuff. Okay? So let's suppose we have. Do you guys hear me? Because Saud is there is no.
Yes, we can hear you.
Okay, Saud, the problem is on your side. There are 2 points, A and B, where f has a local maximum. That is, f of AB is larger than nearby values of f of xy. The larger of two values is the absolute maximum. Okay, so I'm talking about the figure in this slide. Okay, likewise, if f has two local minima, where fab is smaller than the nearby values, the smaller of these two values is what we call the absolute minimum. In fact, we've seen that already in calculus 1. Okay. So by definition, a function of two variables has a local maximum at the point, let's say, AB, if f of xy at any nearby point is less than or equal to f of AB, and it would have, in fact, a maximum if f of xy is larger than f of AB in the neighborhood of AB. Okay? So in the two cases, we say we have a local maximum and a local minimum. Okay. Now, what is absolute? Absolute if this extends to not only to the neighborhood of our point AB, the whole domain of f. So if the inequality in definition 1 holds for all points xy in the domain of f, then f has an absolute maximum or an absolute minimum. Okay. So you have to span the whole domain to be able to conclude that we have absoluteness. We have absolute maximum or absolute minimum. Now, let's see Fermat's theorem for functions of two variables. In fact, Fermat was a famous mathematician, French mathematician. He said that if f has a local maximum or minimum at AB, and the first order partial derivatives of f exist there, then fxab and fyab, which are the first partial derivative of f at our point AB, should be equal to 0. Okay? So we have what we call a stationary point or a critical point, a point where the gradient is equal to 0. Right? The gradient of f here would be equal to the 0 vector. So this is Fermat's theorem for functions of two variables. So a point AB is called, in fact, a critical point or stationary point if f of x AB is equal to 0 and f of y AB equal to 0, the two first partial derivatives. Or, as you see, as we added previously, give me a minute, guys, please. I will get back to you. Okay, guys, thank you for waiting. I had a kind of issue, and it was fixed. So, so if you continue, that theorem in fact says that if f has a local maximum or minimum at AB, then AD is a critical point of f. However, in fact, in single variable calculus, not all critical points give rise to maxima and minima. So the point we were talking about before the interaction, remember that generally we talk in calculus 1 about critical point if the derivative is equal to 0 or the partial derivatives do not exist. Remember, guys, what does that remind you of, guys? What do we mean by points where the partial derivative does not exist? Let's talk about single variable calculus, okay? Now I'm drawing graph, no limit. Yes, but for example, here do you see points that do satisfy this condition? Any point that satisfies this condition here? What happens here at this sharp point? At the sharp point, we have a non-smooth function, right? In fact, the function is not smooth because of something. What happens there, guys? Because the partial derivatives, you remember in calculus 1, we've taken the derivative from the left and the derivative from the right. In fact, the derivative from the left points down, okay, to this side, and the derivative from the right points down to the other side, okay? So if the two vectors are not carried by the same line, I cannot put them in the same line, right? It's impossible. Then the derivative does not exist. Okay? So you may imagine now this is one-dimensional. So you can imagine that in 2D, this might happen too. You can have like no smoothness at some point. So the first partial derivatives do not exist. Okay? So theorem 2, in fact, says that if this happens, and in fact also critical points are points where the first partial derivative is 0 or does not exist. The last point here I'd like to mention on this slide is that at the critical point, the function could have either a local maximum or a local minimum or neither. What do you mean by neither? Do you remember anything that calls to the fact that a function has a first partial derivative that is equal to 0 and is not the point is not a maximum or minimum? How do we call them in calculus form?
Local maximum.
No, this is not. We're saying that it's neither. None of them. It's none of them. It's not the local maximum or local minimum. What should it be?
Is it absolute maximum?
No. Try again. Someone else. Can I help you with drawing? What happens, guys, here? Around this point, what happens? Do we have a zero derivative? Yes, we do. Right? The function is kind of constant, let us say, or it has a horizontal tangent. Am I right? Ah?
Right.
This is what we call in calculus 1. Starts with S. It's a sad point. No, it's not a sad point. It's a saddle point. Ah? This is a saddle point. Okay? Saddle, guys, what does it mean in English? The equivalent in Arabic is search. Okay? Got it? So this might happen at a local minimum and local maximum are at a saddle point. And you can imagine that the same thing could happen with the two variable functions. Okay. So let's take this example, this beautiful example where you have x squared plus y squared minus 2x minus 6y plus 14. And if you differentiate with respect to x, you get 2x minus 2. And if you differentiate with respect to y, you have 2y minus 6. So if you do apply the Fermat's theorem, you have 2x minus 2 equals 0. So x equals how much? And on the other side, you have 2y minus 6 equals 0. Y equals how much? 8. These partial derivatives are equal to 0, where when x equals 1, y equals 3. So this is the critical point. Now, if you complete the square, what do you find here? I mean, we are plugging these values where? We're plugging these values in our function. Okay? Now, if you plug in 1 plus 4, okay? Right? It's 1 plus 9, sorry. Minus 2x minus 6y plus 14. We're trying to work on the function by completing the square. So we are rewriting it like this. You can see now when you plug in 1, 3, what do you find? You find 0. So in fact, what happens at 1, 0, you just minimize the function. So this is the method. Okay? So this is a typical case where, in fact, if you were able to move on or you moved on to second derivatives, what would you find, Charlie? What would be the second derivatives, guys?
Activity up or down?
If you differentiate the second time, you've seen higher order derivatives. You get 2 sum, right? Now derivative of f with respect to y second time is how much? It's 2. And the mixed one, the one where you differentiate, as we said last time, first time with respect to x or with respect to y, you get the same things, And here also you're going to get 0. So what is that beautiful Asian matrix? The Asian matrix, the one that contains the derivatives, is 2, 0, 0, 2, and it is positive definite. Okay? Why it is positive definite? You see the determinant of this first submatrix is 2, positive, and the determinant of the whole matrix is positive. So we say in fact, that all leading determinants, we call them leading determinants, are positive. So the function, in fact, is concave here. Okay? Similarly to what we see in calculus 1. So, in fact, this is a drawing of the function itself. So you see it's concave up. And since x minus 1 squared and y minus 3 squared are both positive, we have fxy greater than 4 for all the values of x and y. Therefore, f13 is equal to 4 is a local minimum, and in fact, it is the absolute minimum. And this can be confirmed geometrically from the graph of f, which is the elliptic parabola with vertex 1, 3, 4, as it is shown here. 4 is the image of the value of f at 1. Okay, so you see, in fact, how optimization helps solving problems, in fact, in practice, and it would be used to solve engineering problems, management problems, or financial problems, actuarial problems. In any application, you will always need mathematics. So here we talk about second derivatives, as we just mentioned in the example. Okay? So second derivatives test. Here, suppose that the second partial derivatives of f are continuous on a disk with center AB. I'll come back to explain why we are working on a disk. And suppose that the first partial derivative at that point AB are zeros. So of course AB is a critical point. And we do define D to be what? To be this. It's the product of the second derivative of f with respect to x. So you see double x here, we differentiate it twice with respect to x. And here the double y, we differentiate twice with respect to y, minus fx. So what is this? This is the determinant of the Hn matrix. This is the determinant of which matrix? The matrix where we wrote fxx, fxy, fyx, fyy. Okay, guys? So the determinant is this one. You see the determinant is going to be fxx times fyy minus fxy squared. Okay? So if this determinant is positive, what do we have? We have a concave function. So we say that we have a local n. Okay? And remember, see, I mentioned that the first entry should be 0, should be strictly positive. So that I have the leading determinant condition. So both conditions that fxx is strictly positive and d is strictly positive, we have a local minimum. If it is the inverse here, that the first one, the last one is positive and the first one is negative, we have a local maximum. Okay? Be careful, huh? So the first entry here is positive, is negative, and the whole determinant is positive, we have a local maximum. Okay? So your problem is inverted. Now, what happens if the determinant is negative? If the determinant is negative, then at that point is neither a local maximum or a local minimum. So in cases, in fact, in case C, the point AB is called what's called a saddle point. You've seen it from the exam or from the explanation. What happens when the derivative is 0, but it's neither a local maximum or a local minimum. Yes? Which means, in fact, at that point, F is crossed by the tangent plane to AB. So now let's generalize and move on to absolute maximum. So what is an absolute maximum and absolute minimum? So for a function of one variable f, remember calculus 1, we've seen the extreme value theorem, which says that if f is continuous on a closed interval AB, then f has an absolute minimum value and an absolute maximum value. And in all cases, if it is continuous, you have always an absolute maximum and an absolute minimum. Okay? So according to the closed interval method, we found these by evaluating f not only at the critical points, but also at the endpoints of AB. Remember, one of the tricks in calculus 1 was that sometimes the absolute maximum or absolute minimum, or both, they do not lie at one of the points where we have the derivative equals 0. They lie at the endpoints. So there is a similar situation for functions of two variables, in fact. And just as a closed interval contains its endpoints, a closed set in R2 is one that contains all the boundary points. Okay? So, what is a boundary point? A boundary point of D is a point AB such that every disk with center AB contains points in D and also points in D. So, points not in D. So, that's why we talk about this. A boundary point of D, since we are here talking about two-dimensional domains, okay? The boundary point of D is a point AB such that every disk with center AB, so suppose this is the disk, and its center is the point AB, contains points in D, okay, and also points not in D, okay? So for instance, the disk where x containing all points xy, where x squared plus y squared is less than 1, what is it? It's the disk with radius equal 1. okay, which consists of all points on the inside of the circle and on the edge of the circle. It is closed. It is a closed set because it contains all of its boundary points, which are the points on the circle x, y squared plus y squared equals 1. Okay? So that's why we are talking about this. So absolute maximum and minimum values. But even one point on the boundary curve were omitted, the set would not be closed. Okay? So these are closed sets. You see this maybe if you take more advanced course in topology of set theory, how we talked about closed sets and stuff like this. For the guys who take minors or majors in math, it's a fundamental. Okay? A bounded set R2 is one that is contained within some disk. Okay? Now I'd like to add a point, guys, and this small window I would like to open could be very useful in the next in your academic career, guys. So what is, guys, do you know what is a convex set? I'd like to talk about a convex set. What is a convex set? What do you mean by convex? I'm sure you've heard this terminology before. Anyone knows this? Without asking Wikipedia, of course.
Curve outwards? Something.
Well, when we talk about curves, yes, it's in fact when we curve-wise, when we talk about curves, for example, this is a curve which is convex. No, it's not convex. This is what we call concave, or what we call generally concave up. Okay, and in fact, in the opposite case where it is concave down is a case where we have what? Convex. Convex. What is a convex set? It's simply, it is a set where every 2 points, every combination of the 2 points, and the whole segment, if we draw the segment AB, it belongs to the set itself. Okay? This set is convex because for every pair of points in my set, if I draw this segment AB, it is in my set. No segment is in my set. So this is convex, while this one, what do you think? This one is not convex. You see, if I take 2 points from the 2 different sides, some points are inside the set sometimes, some points are not. Okay? So this set is not convex, it is what we call concave. Okay? So generally, in fact, work optimization, we do prefer, we'd love to work on convex sets because we can iterate, we can work inside the domain with risking to be outside of the domain just because of some wrong step or some wrong jump. Okay? That's what I wanted to add about convex sets. So you do understand that it's very simple to understand it, that when we talk about convex sets, it's just taking any pair of points, take any combination of them, just simply figure out, you draw in a segment, basically the 2 points. In fact, the whole segment is still inside your set. Okay? So, in other words, in fact, if you go back to talk about maximum and minimum values, we have what we call the extreme value theorem for functions of 2 variables. We say that if f is continuous on a closed and bounded disk in R square, then f attains an absolute maximum value at x1, y1, and an absolute maximum value at x2, y2, at some point, x1, y1, and x2, y2. Okay? So there is always, by definition, an absolute max and absolute minimum. So this is the extension to 2 variable functions of the extreme value theorem we've seen in calculus 1. Okay? So there is a couple of definitions to follow, but the procedure, in fact, how to operate to find the absolute maximum or the absolute minimum values. So mention what we should do. Find the value of f where we have a critical point, so you find the derivative equal to 0 or the derivative is not defined. Okay? you find the extreme values of f on the boundary points. So you have to find the endpoints and compare the values at the endpoints with the values at the critical points and pick the best ones. The max for the max and the min for the min. Okay? To conclude which one is the max and which one the absolute. Okay? So for example here, I have in this example 7, I have f of xy equals x squared minus 2xy plus 2y. Okay? On the rectangle, which is defined by what? It's defined by, see, I have a convex set here. That's why I was talking about convex sets. It's x between 0 and 3, and y is between 0 and 2. So basically, I have a rectangle, and you see that this rectangle is convex. If you draw any line reaching any pair of points inside my rectangle, you will be obliged to stay on, to be kept on the set itself. Okay, so we'll do a convex optimization. So first of all, let's compute the first partial derivatives. Now, what is the first partial derivative here with respect to x? Ahead. Are you with us?
Yes.
What is the first partial derivative with respect to x? It's just in front of you. Saud, are you with us? Do you know how to compute the first partial derivative, yes, Saud? Yahya, do you know how to compute the first partial derivative?
Yes, sir.
Yes. Can you compute the first partial derivatives here?
First partial derivative for this function, sir?
Yes, sir.
Okay. For f of x, right? 2x minus 2y plus, 0. That's it.
Okay. And for the first partial derivative with respect to y, yes, Saud. Ready? Can you do it now? Ali, yalla, go ahead, Ali. I mean, this is a very old material. What are you going to do this next week? Just rush, and try to work and understand concepts that have been covered for 3 weeks or 4 weeks ago? Okay, so these are, so to find the critical points, we find the critical point here, those that make the derivative equals to 0. We find them at 1, 1, in fact. Okay? And then we look at the values of f on the boundaries of D. So you see now we have a drawing. These are the boundaries of D. And you see the first boundary given by L1, the first segment, L1, is the boundary where y is equal to 0. And x is between 0 and 3. Okay? Then we have L2, where x is equal to 3, and y is between 0 and 2. We have L3, where y is equal to 2 and x is between 0 and 3. And here the last one, L4, where x is equal to 0 and y is between 0 and 2. Okay? Got it? Okay. So if we work on these, on L1, we have y equal to 0, which means what is the value of the function anyways is going to be equal to x squared. Okay? Now, what do we want to do? We want to the maximum. So for sure the maximum is at 3. Okay? Now, the maximum at that boundary is at 3. Now compare to the value you found at f11. What was f of x? F of x was x squared minus 2xy plus 2. So at 1, 1, it's 1 minus 2 plus 2. Right? So it's 1. Which means the the maximum now has been improved. Okay? So what happens? This is increasing for the function f of x. So its minimum value, in fact, would be at 0, because on the line 1, you get the minimum at 0 and the max at 3. Okay? On L2, we have x equals to 3, which is constant, so it changes the pattern for f. You see, now we have 9 minus for y, so for sure, you see, because of the negative, now it's inverted. The maximum would be at the lower limit, so the maximum would be at 0, at y equal to 0, and the minimum would be at 2. You see now the maximum here on L2 is 9 also. Okay? This is a decreasing function of y, so its maximum value is f30, the same point we found before on L1. In fact, it's the intersection of L1 and L2. That point where you have x equal to 0, x equals to 3, y equal to 0. And the minimum now is at 3, 2. And if you continue on L3, we have y equals to 2. You can simply observe that f of x2 is equal to x minus 2 squared, and we see that the minimum value of this function at 2, 2 is 0, and the maximum is 0. Okay? So basically, we were able to study with L4, to study the whole function on the whole domain. So what you can do now is recapitulate, collect all the information you had, and conclude what are the maximum and the minimum values. So the maximum value on L4 is 0, 2, so you get 4, and the minimum value is 0. So that's on the boundary, the minimum value of f is 0, and the maximum is 9, which was found at 3. Okay? Okay, guys, and this is just here on with the drawing of the function itself, and which is x squared minus 2xy plus 2, and the domain of which is the rectangle. And you see that the maximum would be at this point 0, and the minimum would be in fact at 0. Okay? So, guys, I'd like to move on and give you a question from the book, and I'll take the attendance. So basically, I will stop the recording just now. Okay.